Howdy, cosmonauts. We're going to be going over now questions that have to do with orbits, right? But now we already talked about what if the problem that you're doing asks you about changes or whatever to do with orbital speed. But what if it asks you about the period, right? If it talks about the period, capital T, of the orbit, right? How does the period change, or what is the new period like compared to the old period, or whatever? It's a really similar process. It's the exact same process, actually. The only difference is we're going to use a different expression, because before we used centripetal acceleration is equal to v squared over r, right? And that doesn't have a period in there for us to solve for. So we need to use centripetal acceleration in terms of period. And so the other way we could do that is there's another expression we can do. And if you don't know where this is coming from, I'll link a video in the description down below where we figure out how to make this equation. But the equation for centripetal acceleration that has period in it is 4 pi squared times the radius, or the distance between those two things, divided by period squared. Okay? And from there, now our process is really similar. Force of gravity is my only force, so that's responsible for the entire net force. I would plug in Newton's law of gravitation. The two masses divided by their distance squared, and now I have mass of the satellite times 4 pi squared times their distance divided by period squared. There's a whole bunch of stuff going on here, and if you want to see this specifically, broken down, we can go over it in class. You can come see me, but this ends up, if I solve for period here, this ends up turning into the period of the orbit is equal to 2 pi times the distance between them to the power of 3 over 2, all divided by the square root of g times the mass of the planet. Okay, now this is a lot uglier than our speed equation, just because there's like weird exponents, there's square roots and denominators and all that, but this is what we end up looking like if you're trying to solve for orbital period. Okay, now again, just looking at what this means, this tells us a few things. This tells me that the period is proportional to remember 2 pi is just a constant, so it doesn't affect anything, it's just a number. But this tells me it's proportional to the 3 over 2 power of the radius, right? And this also tells me the other thing is, remember, g is the gravitation constant. That's just a number. But the variable here, mass, that tells me that period is inversely proportional to 1 over the mass of the planet that's pulling on. In this case, I have mass of the Earth, but it could be any planet that it's orbiting, right? It's just in all of these examples, it's mass of the Earth. Okay? Now notice, again, just like with orbital speed, the mass of the actual satellite or orbiting moon or whatever it is, whatever the object is that's orbiting, that mass is gone from this equation. It has nothing to do with the period at all. If I made this satellite 4 times as mass, if I increase the mass by anything, if I change the mass by anything, the period would stay the exact same, because the mass of the satellite has nothing to do with it. Okay? So this is the equation we're going to use to go through some examples, and this is how we derive that equation. Same process, right? It's just now we use a different equation for our centripetal acceleration.